Great. Firstly, of course, I'd like to thank the organizers, Helen and Thomas, for allowing us to show some of the work that we're doing. And this really, a lot of the stuff that we're doing is work in progress. So many things you will see that suddenly I'll stop and you'll expect another transparency. And that just shows you where we are at the moment. And I think at that point, it's also a good moment in time to actually thank Jairo for putting together all the SPICE workshops. So I think that's done a lot of good to the community. So I'm going to talk about three types of magnetic ordering. And of course, in the end, we're very interested in these really intrinsic antiferromagnets. And it just turns out that it's very tough. So a lot of the times we either go to ferrimagnets or synthetic antiferromagnets, where a lot of the technique that we're always using can be employed. So first a little bit on spin orbit torques. And then some measurements on spin orbit torques and synthetic antiferromagnets. And then I'll show you quite a little bit how much pain it is to actually make such a material. And we had this very nice talk from colleagues doing this copper manganese arsenide, which I can really feel because we've gone through some of the same pain here. And then finally, I'll show you some transport. Firstly, the transport generated intrinsically in ferri and antiferromagnets, and then spin transport across antiferromagnets, and a little bit how this differs in metals and in insulators. So very, very basically, okay, you know that there are typically different types of antiferromagnetic order. And the idea is that they're not susceptible to stray fields. There's no dipolar interaction. It's actually not fully true. So here's a paper, a theory paper. And don't be scared, I'm a co-author, but really Helen and Jairo also co-authors, so it's okay. So you can read up how you can manipulate antiferromagnets using fields. And then, okay, there's this ultra-fast dynamics, of course, the magnon frequencies in the terahertz range, but also fundamentally the spin structure dynamics is only limited by the velocity of the magnons, which is like 100 kilometers per second, 10 kilometers per second, because there's no Walker breakdown. So this is really a fundamental advantage that for someone that comes from a background of domain walls and Skyrmions makes this very exciting. So we have kind of the first path towards an antiferromagnet is to look at the synthetic antiferromagnet, which is really two ferromagnets. So you've got a proper ferromagnet here and a proper ferromagnet there. They're just coupled by RKKY in an antiferromagnetic manner. And they, in many senses, can actually emulate an antiferromagnet. But the nice thing is that many times you can still detect one of the layers independently. Then there are proper antiferromagnets. So, here's an antiferromagnetic Skyrmion. And then there are ferrimagnets at the compensation point, where there is a difference to the antiferromagnet in that different sublattices actually are still ferromagnetic in themselves. So the gadolinium is still coupled ferromagnetically to the gadolinium, and the iron lattices are coupled ferromagnetically or antiferromagnetically to one another, but the overall magnetic moment is zero. So this can actually lead to distinctly different dynamics from an antiferromagnet, but some of the effects are again similar. And if we want to manipulate these, then the most obvious approach now is spin orbit torques. You've already seen a little bit of theory, so I just wanted to show you a few very basic slides where you have here an antiferromagnet or ferromagnet, and then you have a heavy metal layer with strong spin orbit interaction, and then you generate by the spin Hall effect, which converts a charge current into a spin current, you generate a spin accumulation here at the interface to the magnet, and then it diffuses across the interface and it manipulates the ferromagnet or antiferromagnet. And the nice thing is that since you have this damping-like torque, which is M cross something, so it's a staggered torque that actually manipulates the magnetization even in an antiferromagnet, the Néel order parameter, even in an antiferromagnet here. And you saw the talk by Tobias about measuring this using terahertz. So we have damping-like and field-like torques, and just from the symmetry one has to remember, so if you have an interfacial or a torque that is generated from an adjacent layer, only the damping-like torque will play a role because it has the right symmetry for the antiferromagnets, and if you have a bulk staggered torque, then it'll be the field-like torque that plays a role. So that's quite different than in a ferromagnet. And then in addition, you have in a such a multilayer also an interfacial effect, this inverse spin galvanic effect, where you generate a non-equilibrium spin density at the interface, which manipulates then again the magnetization. So these can then act on ferromagnets or antiferromagnets or synthetic antiferromagnets. So how do we then measure these? Oh, yeah, and then these, in addition to these multilayers, also in bulk systems where you have bulk inversion asymmetries, such as in the paper by Chiara, you can also get kind of bulk inverse spin galvanic effect torques. And then there are different methods to actually detect it. So now I'm really back to the experiment. And these are sometimes applicable to antiferromagnets, but not always. For instance, this current field equivalence does not work, where you measure the equivalent effective field acting on the antiferromagnet, because you would have to measure a staggered field, which doesn't exist, or a staggered external field. But second harmonic detection and other approaches can work. And just here is lots of nice papers of people that have demonstrated that in ferromagnets and some in antiferromagnets. So what we're going to do is we are going to look at synthetic antiferromagnets. So this is a collaboration with some groups in Korea based on some of the pioneering work of Stewart's group, where they've shown that in such a synthetic antiferromagnet, you can obtain very fast domain wall motion. So they showed if you have a multilayer of, in their case, it's not cobalt silicon boron, but in our case it's cobalt silicon boron, and you couple them parallel or anti-parallel, on the coupling strength changes, then the velocity of the domain walls can change. So there is something happening beyond the typical, say, spin orbit torques, because the platinum that generates the spin orbit torques is the same in both cases. And just to show you that indeed these multi-layers couple, so if they're for strong fields, both layers are parallel, and then when you reduce the field before you get to 0, these two layers couple antiferromagnetically, so there's a plateau where there's 0 net magnetization, and then you can push them again in the opposite direction. This field here just shows you the strength of this RKKY coupling. So by varying the thickness of the platinum, and that's something that was also new to me. Everyone uses ruthenium, but it turns out that platinum also mediates the RKKY interaction. Again, look at Stewart's 1996 papers or 1999 papers. He's gone through the whole periodic table and measured RKKY, and it turns out lots of the materials show RKKY. Just ruthenium is better and is stronger, therefore everyone uses ruthenium. So for very low platinum interlayer thickness, you don't see any antiferromagnetic coupling. Then if you increase the thickness, you get this nice antiferromagnetic coupling with different strength. And then if you make it very thick, then you go back to the ferromagnetic coupling. So you have this oscillatory RKKY coupling, just as in the case with ruthenium. And now you can measure the spin orbit torques using the second harmonics, where you measure the first harmonic in a Hall cross and the second harmonics, and then you can deduce with some fancy math, and there's some corrections introduced by Kevin Garello and Masahitsu Hayashi to get rid of some artifacts, but fundamentally you can then deduce both the longitudinal and the transverse, so the damping-like and the field-like torque, and they have the right symmetry. The longitudinal torque changes its direction if you change the magnetization, and the transverse stays the same within our error bars. And then you can determine the torque, and it turns out that the torque is rather large. You see here, this is 11 millitesla per 10 to the 11 amps per square meter. So this is one of the strongest damping-like torques that we have seen. And then we are on it at the moment. This is the work of Kyujun, to actually understand how this depends on the coupling. So this is one of the things that Stewart has this exchange torque model, and I'm not completely convinced, but that's something that we're doing right now, and there you'd expect now another slide, but that's it. So we have it for some of the layers, but not for all, and now the next step is obviously to look at it. Is it different if you're antiferromagnetically coupled or ferromagnetically? Right. Now, of course, you also want spin structures in these antiferromagnets. So far, what I showed you was just single domain states, so nothing new in terms of spin structures. But there's this nice work by Joe and Oleg showing that you can have, well, theoretically, antiferromagnetic skyrmions, and then for beginners like ourselves, also in synthetic antiferromagnets, you can have antiferromagnetic skyrmions. Now the question is, why should we bother? It's, as you saw, it's a hassle to make these materials. So why, if you're interested in skyrmions, should you go to antiferromagnets? And the reason is the following. It's this one here. So now this here, you have 3 skyrmions initially in the center of our racetrack. And you inject the current along the direction of the wire. And then what happens is that these 3 skyrmions don't move along the current direction, but they actually move at an angle. And so this is a problem, because if you push them with enough current, they're actually being pushed out of the edge of our wire. And now all this mumble-jumble about having topological protection doesn't hold in a non-infinite continuous layer. So here you can destroy skyrmions pretty easily. So that's not good. And you can see that actually also experimentally. So we did in this work, we did some imaging where we saw that actually we lose skyrmions. So here in this movie, we start, let's just wait until it starts, we start with 5 skyrmions. And then after a while, there's only a couple of skyrmions left. And so there are different problems. And one problem is that we push them out of the edge of the wire. And to directly demonstrate this, we actually did some high-resolution time-resolved imaging. So this work by Kläui and others, where we show that we can image the direction of the skyrmions in real time, back and forth. And now it looks, it looks like, since I plotted this, it looks like, it's moving parallel to the current. But actually, the real current direction is at an angle. So they move at an angle. And it just turns out that in this wire, it's very wide. And so it looks like they're happily moving along your wire, but they're moving at an angle. And this was also shown by Axel's group in this paper, that depending on the current density, this angle even changes. So this is a pain. But if you're interested, so here's our paper. And we look at the flow regime. Axel looks at the creep regime. So what can we do? So this is going to be really a showstopper for a lot of the skyrmion-based racetrack. And then, you need to think about where does this skyrmion Hall angle, where does that come from? And it comes from the topology of the skyrmion. But what you can also see is that if you have two of these, layers which have opposite magnetization, then the skyrmion in this layer will move this way, and in this layer it will move this way. And now you can already guess, if you couple them, then they will both move happily along the current direction, because you force them to stay on top of one another by being a synthetic antiferromagnet. And then you can do things like that. And that, I think, is something which is very exciting, because this, I think, is a key advantage of skyrmions over domain walls, because you can move them around corners and crosses easily. So here in this paper, which just came out last week, there are a lot of ideas for devices. And you can see that this skyrmion now, it can be moved around the corner, but you can think about moving it in a complex, matrix system. So you can move it in such a, along multiple corners by setting the current path. And this is only possible if you have two coupled skyrmions. So these are the 2 layers of a synthetic antiferromagnet. So it's a simulation that Kai did, where you see that the 2 skyrmions, they're always at the same position. And only because they are coupled, you can actually move them reasonably reliably around corners. If you try to do the same simulation with a single layer, they will not go around the corner. They will be annihilated at the edge or at the corner here. So this is a huge advantage. And I think it's something you can only do with skyrmions and only with antiferromagnetic skyrmions. So as a motivation, I think this serves rather well to look at skyrmions and antiferromagnetic systems. Okay, again, you'd probably wait for the experimental realization slide. It's not going to come, because we're still on it. But for that, you need, of course, nice materials. So we've seen synthetic antiferromagnets already. And then we spent a lot of time doing real antiferromagnets, well, like intrinsic antiferromagnets. And so this was based on a motivation by the paper by Thomas and Hyro, that manganese to gold is good. And this is really the project of Alexis Saposnik. He had a poster here, and it's done together with Hajo Elmas, Hartmut Zabel, and Martin Jordan. So we worked on depositing this material and understanding the techniques, in particular trying to set the spin structures of that material. So first you grow these, and Martin did a very good job in his cluster to optimize the growth together with the PhD students. And you see it has like nice in-plane surface order. You do X-rays, and it's really manganese to gold. And it turns out, at least he tells me, the growth isn't all that difficult compared to some of the other compounds. And you can get reasonably good quality layers with a reasonable amount of effort. Then what you do is you want to check what is the spin structure. And of course, as an antiferromagnet, you cannot directly image the spin structure. So the first thing we did is we put some iron on top, and we look at domain imprinting. So we have thick manganese to gold and a little bit on iron on top. So this was published in this paper here. And then we see at saturation, this is all, the magnetic contrast is saturated. But then at the coercivity, you see something that in iron you wouldn't expect. So this is just the iron image with the Kern microscope. And we also did some PEM. And we see some micron-sized domains. And this, a single layer of iron wouldn't do. And so the interpretation is here that we see the domains of the manganese to gold imprinted into the iron. And you see it's a mess. Lots and lots of small domains, or relatively small domains. So you need to somehow be able to set the spin structure of that material. And so how can you do it? Well, the first idea is, of course, you can apply a field and use the spin flop transition. So these are some slides from Alexei, which he nicely did in animation. If you apply a strong field, then the magnetization, the antiferromagnetic magnetization, the manganese to gold, will align perpendicularly to the field. If you then apply the field perpendicular, then the spins will just cant a little bit, but go back. So this is good. However, it's not going to work with your normal permanent magnet. So you need to make a bit more of an effort. And so we went to the high field magnet lab, also actually Alexei did, to Dresden, where they can have 70 Tesla. So you have to hold your sample into the 70 Tesla at 10 milliseconds, which is not so super convenient for devices, but it's still exciting. And then it turns out you get also nice exchange bias, so it looks like there's no random domains of the manganese to gold. But really the demonstration that this really works is direct probing of the nail order parameter, which you can do by XMLD. So then together with Hartmut, we went to the synchrotron and we did XMLD. And you see indeed our sample, which had seen the 70 Tesla, shows a very nice XMLD peak. And to show you that this is really an alignment of the nail vector, we turn the sample by 90 degrees, and then you see the contrast reverses. So here it's down up, and here it's up down. So this is really what you expect in XMLD. 90 degrees gives you the black-white contrast. And just to check that this is not happening for any sample, if you don't put your sample in the 70 Tesla, then it's pretty flat. There's nothing that you can see. So you just have lots of domains which are randomly oriented. OK, so now using the 70 Tesla is not ideal. If you want to do experiments, you can't drive to Dresden every time. It's a bit of a hassle from Mainz, at least. So you need to find a way in order to set a single domain structure of the manganese to gold. And so there, what do you do in a ferromagnet? Well, you apply a field. Or what you can do is you can also use strain to induce an anisotropy. So then the way forward is to go to strain. And so we built a small strain device where we can actually monitor the strain with the strain gauge. And you can put your sample here on top. And then, like in this medieval torture instrument, you can adjust the screws. And if you adjust it too little, the sample dies. So you have to be careful, but you can apply like 0.1% of strain, which for a ferromagnet yields significant changes for the anisotropy. And so that's what we did. And then we did, and the nice thing also, it's compatible with UHV conditions, so you can do it really in UHV, for instance, in a synchrotron environment. And then what you can do is in the unstrained sample, you have like not much visible XMLD. And then if you strain the sample, indeed, you get this typical peak of an aligned sample. So this really is good. It means that using strain, you can generate an alignment of the domains in one direction. So you might still have anti-phase boundaries, but at least you have all the nail vectors oriented in one direction. And then based on that, you can then do the experiments and look at, for instance, spin orbit torques and things like that, which so far were hampered by the fact that we always had kind of random magnetization or random nail vectors. OK, and now you expect the next slide, and it's not going to come because we're still on it. All right, so at least, but I mean, this, we're talking about 3 years of work. This is not something that came overnight. OK, and then just to show you that we also work on some other materials. I mean, manganese to gold is great, but we're also interested in some lower conductivity materials for various reasons. So nitrides is a work with Tetsuya from Nagoya, who's spending some time as a visiting scientist with us. And one of the nice things that they saw is that you can actually switch exchange bias electrically. So in such a multi-layer of manganese 3 gallium nitride and cobalt, iron nitride, which is a ferromagnet, you can switch the exchange bias by applying fields. So this is interesting. And we are looking at this material now for spin orbitronics in antiferromagnets. OK, and now finally, let's come to transport in and transport through ferromagnets and antiferromagnets. So what we're here doing is we're looking at spin transport due to thermal spin currents and spin pumping. So this is a ferrimagnet. This is gadolinium iron garnet. For those of you that don't live in a ferrimagnetic world, what happens is that at low temperatures, the gadolinium is dominating the overall magnetic moment. And then as you increase the temperature, the gadolinium moment goes down. And then you see here the magnetization is a function of temperature. At this compensation point, the gadolinium moment together with the ion A side moment just compensates the ion D side moment, so the total magnetization is 0. And then if you go to even higher temperatures, the gadolinium moment is so small that the ion D side wins. And so above here, the magnetization is always aligned so that the ion D side is parallel to the field, and here always the gadolinium is parallel to the field. And now, if you measure the spin current, it turns out that the spin current here as a function of temperature looks very different from the magnetization. You might have thought that at the compensation temperature, where the magnetization reverses, the spin current reverses, and that happens. However, at low temperature, it turns out that around 80 Kelvin, the spin current again changes its sign. And that was something that was very surprising. And as you see here from this All-Stars paper, it took us a lot of effort and a lot of brain power from theory and experiment to actually understand this. And what happens is that there are two mechanisms that can happen. That at very low temperature, where the gadolinium moments win, that the spin transmission across the interface for iron and gadolinium is not the same. And furthermore, Joe Barker did some nice calculations to also show that the occupation of the different magnon modes also changes with temperature, which can explain this effect. Again, I don't want to go into the details, it's all in there. But the important thing is that the spin current does not simply mirror the total magnetization. And that's important for all the antiferromagnetics people, because it means that in an antiferromagnet, not all is lost. So you can generate spin currents even if you have no net magnetic moment. And so that is something that we then tried, for instance, for strontium iridate. And you see there is a nice spin-Seebeck effect at high fields, even with below the spin flop transition. And that's something we are studying at the moment. Now, this antiferromagnets, you can generate spin currents in the antiferromagnets due to the spin-Seebeck effect, or you can transport an existing spin current across an antiferromagnet. And that's the last part of my talk. I want to look at transport across antiferromagnetic insulators and antiferromagnetic metals. So we have a ferromagnet or ferrimagnet that generates the spin current. We have an antiferromagnet, which is the interlayer, and then we have a detector layer, which usually is platinum. And now we vary this antiferromagnetic material, which can be an insulator or metal, and we vary the generation of the spin current, which can be spin pumping or thermal spin currents. So the first thing is that a lot of people looked at nickel oxide, and the surprising, I think the first finding was in this paper and later here as well, is that at a finite thickness of nickel oxide, there's an increase of the signal compared to no nickel oxide. So no interlayer is worse than some interlayer, which is very unusual in magnetism. You put an interlayer and things go up. So it's, it looks like it's some active component, and there are a lot of theories now. And it turns out it's not so universal. If you look at single crystalline YIG with nickel oxide on top versus polycrystalline nickel oxide on YIG, here you don't see the increase, here you see the increase. So that's something that's not completely clear. Secondly, and this was done using spin pumping. Secondly, also people use thermal spin currents. And then you see that as a function of temperature, you have a peak of the signal, the transmitted signal, at roughly the Néel temperature. And there have been a lot of theories about this enhancement using spin fluctuations. So here in this paper from the Sendai group. And then there are also things about the spin conductivity across the interfaces. And we see similar effects using nickel oxide on YIG, where you have this peak roughly at the Néel temperature. So what we're really interested in is now to see what happens in metals. In insulators, it's pretty clear the spin current can only be transported by magnons. In metals, that's not the case. In metals, you can also just put electrons across. So the question is, in a metal, do we have transport by the magnon, which still exists, or do we have transport just by conduction electrons? So what we do is we compare platinum and iridium manganese, which is a well-known antiferromagnet, on top of YIG. YIG is just the generator of a spin current by the spin-Seebeck effect, and platinum is just the detector. So firstly, what we do is we put our multi-layer in our setup, where we have here a heater, and here we have a cooler, or just nothing, no heater. It's in a cryostat, and then we measure the signal that is generated in the platinum on top, which is just the spin current that is generated. And we also do spin-Hall magnetoresistance because this is a nice complementary measurement, because in the spin-Seebeck effect measurement, we just measure the current that goes from the YIG up. And in the spin-Hall magnetoresistance measurement, we measure the signal that comes from the platinum, goes through to the YIG, and goes back. And the question is, is it conduction electrons or magnetic excitations? And so here is our results. And there's one more thing, of course, iridium manganese can have a spin-Hall effect. So that's something we also checked. I'll come to that in a minute. So what we did is we looked firstly at YIG platinum. So it shows this temperature dependent. If you're interested, we just published it in this paper, which explains that there's a peak at low temperature. However, the interesting thing is we put a little bit of metallic iridium manganese in between, and we see an increase in the signal. So this means also metallic antiferromagnets can generate an increase of the signal compared to no antiferromagnet. Secondly, we see that this low temperature enhancement, which here is at 100 Kelvin, moves to other temperatures, and somehow this also flattens out. And what is very striking is that here at low temperatures, there's abrupt decay. So we have this change in the peak temperature, and it cannot come from the YIG because the YIG is the same. So it's the same YIG piece, it's one wafer from which all the pieces were cut. So the generation of the spin current has to be the same. So this temperature dependence must come from the different iridium manganese. And you see even a little bit of difference in the iridium manganese thickness changes the peak temperature. And so this was also seen here in this paper, where they see that this critical temperature increases with the iridium manganese thickness, which is attributed to the Néel temperature. So we then checked, of course, iridium manganese on its own, because it can have a spin-Hall effect. It has a tiny spin-Hall effect. You actually see a signal, but it's really small. And it turns out if you put platinum on top of this iridium manganese, the platinum has such a low resistivity compared to the iridium manganese that's absolutely negligible. So everything we measure is really the signal that has come into the platinum. So the iridium manganese makes a 2% change. So this is good. In the beginning, I was worried when the student said, let's use iridium manganese because we got it in the sputter chamber. I was like, yeah, but then it's difficult to disentangle. And he said, yeah, I calculated it's 1%. I said, OK, you do it. Right. OK, and so here we look now at the temperature dependence of this spin-Seebeck effect for the iridium manganese two thicknesses. And we see that, and we compare the SMR, and we see they're pretty similar. Yeah? So this really means that it's the transport across the iridium manganese that sets the temperature dependence. And then we measured, we thought like we tried to measure what is the Néel temperature. Okay, the first thing we did was we put iridium manganese on YIG, and obviously, 1.3 nanometers of iridium manganese aren't going to pin 4 micrometers of YIG. We tried nonetheless, and we failed. That's okay. And then we put the same amount of iridium manganese and put a little bit of cobalt iron on top, and there we get nice exchange bias, and we see that we get roughly 70, 80 Kelvin of Néel temperature. And so this is about the temperature where this dramatic reduction in the signal sets in. So this means that the Néel temperature here really shows you at temperatures below the Néel temperature, the spin transport is blocked. And the question is, what is the origin? So we looked at iridium manganese. I didn't know so much about iridium manganese, but then I realized that we started immediately with the most complex spin structure that you could get. We had it in the sputter chamber, so we probably wouldn't even have started with something else if we had known. But wow, okay, at least it shows you that it's not collinear, so it will have, in the polycrystalline case, an equally complex spin structure. And also what is interesting that in iridium manganese, people don't see this maximum of the magnetic susceptibility that you see, for instance, in nickel oxide. So this is measured here in 1974, so we are at 0.2. So there is only a small change in susceptibility. So this might that possibly the spin fluctuations at the Néel temperature are not the dominating factor. And so from our current understanding is that this strong suppression at low temperatures is due to the reduction of the spin transport by thermal magnons. So we have a lot of discussion with Helen and trying to figure now out how we can disentangle the effect of the charge carriers. All right, that's it. So I'd like to thank in particular the people that were involved, so people that did all the transport across insulators and the Skyrmion work and the work on the synthetic antiferromagnets, in particular Martin Joran, who in my group drives a lot of the work, and Hartmut Zabel. And then, yeah, we have a lot of collaborations. So people at the MPIP, people in Korea that make the synthetic antiferromagnets, and Tobias group at Fritz Haber. Then people in Garching, where we do a lot of the spin-Seebeck effect work with. People in Japan that help us in particular with theory input, but also with some of the growth of the antiferromagnets. And then in Mainz, so Alexei, Hajo Elmas, Helen, and Jairo, of course. Okay, this is the funding, and so to sum it up, so spin-orbit effects can occur in this antiferromagnetically coupled system. That's good news. The spin-orbit torques in synthetic antiferromagnets can be very large, and if you have skyrmions in synthetic antiferromagnets or real antiferromagnets, that's really going to enable new devices. And antiferromagnetic materials with bulk spin-orbit torques have been developed, such as manganese to gold, waiting for the demonstration of the spin-orbit torques. And then the thermal spin currents can be transported insulating, but also metallic antiferromagnets. We get an enhancement even for metallic antiferromagnets. And at the moment, the question is, what is the effect of the magnons compared to the charge carriers? And with that, I thank you for your attention.